To map the stars, construct monumental architecture, and manage early trade, ancient civilizations had to process large amounts of data. But as their societies scaled, their mathematics hit a hard structural limit. Look at the Roman numeral system. It operates on an additive architecture. To represent larger values, you just stack another symbol next to it. This creates a fatal scaling issue. There is no fixed limit to the types of digits. Every time your data grows by an order of magnitude, you have to invent and memorize a new symbol. Try running a basic calculation, like multiplying 397 by itself, using only these symbols. The notation expands outward rapidly. It becomes a cluttered, unmanageable sequence where the physical space required to process the data outpaces the calculation itself. Ancient Indian scholars mapping vast planetary movements recognized this computational bottleneck. They realized that adding more symbols wouldn't solve the processing problem. They needed to engineer a completely new numerical architecture. Their solution was the decimal place value system. They restricted the entire operating environment to just 9 distinct symbols. By assigning these symbols to a grid, ones, tens, hundreds, a symbol's value multiplies dynamically, purely based on its position. This positional logic bypassed the bottleneck entirely. Complex arithmetic that physically broke down in the Roman system now immediately resolves in a compact, highly algorithmic sequence. This framework was deployed early to manage massive data sets. The Lalitavastara Sutra, for instance, records an explicit vocabulary for numbers scaling all the way up to 10 to the 53rd power. This was a necessary, scalable hardware upgrade for processing human knowledge. But to function flawlessly without collapsing, this grid architecture required one highly specific missing component. In a strict positional system, an empty column is a liability. If you have the number 101 and you lack a way to securely indicate the empty tens column, the digits collapse together into 11. The concept of shunya, or zero, began as a mechanical necessity to prevent this. It was a literal physical void, an empty space intentionally left on a counting board or a blank rod on an abacus to hold the positional structure intact. Eventually, this physical absence was encoded into a recorded glyph. Archaeological records, like the inscriptions at Gwalior and the Bakhshali manuscript, show this placeholder symbol becoming standard notation. In 628 CE, Brahmagupta transformed this void into an active participant. He redefined zero as a standalone number with its own set of mathematical properties. Brahmagupta engineered the precise operational logic for this new variable. He established the strict mathematical rules for how zero interacts with other numbers. This specific type of computational logic had deep roots. As early as the 2nd century BCE, the scholar Pingala authored the Chanda Shastra, utilizing the concept of zero to build exact binary sequences for poetic meters. By defining zero mathematically, Brahmagupta provided the operational logic that allowed mathematics to advance past basic geometry into complex algebra and eventually the calculus required to model the physical universe. With a robust numeral architecture in place, mathematicians like Aryabhata used it to process the exact orbital mechanics of the celestial sphere. This required extreme precision. Aryabhata calculated the value of pi to 3.1416. This was the exact output of a rigorous, repeatable algorithm. To achieve this resolution, he deployed a polygon doubling algorithm. By continuously multiplying the number of sides of a polygon inscribed within a circle, the geometry physically closes the gap to the circle's true circumference. But this level of complexity introduces a storage problem. Without physical hard drives, how do you store and transmit data-heavy algorithms over centuries without the data corrupting? The solution was the sutras. These verses functioned as highly sophisticated data compression. They encoded massive geometric and algebraic rules into a condensed, easily memorizable oral format. This compressed code could then be unpacked to dictate strict physical engineering constraints. The construction of the Shianachiti, a falcon-shaped altar, required compiling exact numbers of specifically shaped bricks to satisfy complex geometric areas, all transmitted through these strict numerical rules. Ancient Indian mathematicians operated much like early software developers. They compiled complex logic into executable, oral formats explicitly designed to outlast physical media. Because this computational package was highly efficient, it became inherently exportable. By the 8th century, the Indian numeral system migrated westward into the Abbasid Caliphate, its supercharged Islamic science, eventually breaching Europe by the 11th century, where its processing power definitively obsoleted the Roman system. The positional logic refined in these ancient texts became the blueprint for data management across centuries. By the 20th century, this same grid-based architecture was physicalized into IBM punch cards. Each punch or void represented a discrete positional value, the same logic required for modern machine processing. The entire foundation of binary code requires the discrete variables of 1 and 0. Without Brahmagupta's strict rules governing the active presence and absence of 0 as a valid operator, modern machine logic cannot compile. The Indian decimal place value system and the operational 0 constitute the core syntax of modern mathematics. From standard bookkeeping to the orbital modeling of the solar system, every modern calculation relies on this foundational 10-symbol architecture.